let me talk about the midterm. Yeah. Next week, spring break, right? Yeah. Let me bring up the calendar here. Yeah, this is the calendar. So you can see. Yeah, so this week, after this week, next week, this whole week, the spring break. All right. So then our midterm will be after spring break. Okay, the week after spring break. Yeah, I want to put it second class. Yeah, let's say 20th Thursday. Yeah, March 20th Thursday. Yeah. So you know, yeah. Because right now you are still working on homework assignment number 2. So you need to complete homework assignment number 2. Then we need to do review. Yeah. So we need to do a review session and yeah. So then get you ready for the midterm. So review this Thursday. Thursday, I can use the second half to do review. Okay, first half, so we finished part C. Yeah, today we finish part B, then we start part C. So Thursday we need to finish part C, then we do first part of the review. Okay, review. First part I will explain the quiz questions. Yeah. All the quiz questions, first part. All right. So then you have spring break, so you do preparation, and I post the answers to the first assignment. Yeah. So you study. Yeah. Yeah. But the second answer to the second assignment, I need to post sometime in the spring break. Yeah, because you need to use also. So then, after the spring break, the first class, Tuesday, on March the 18th, I need to do the review in this class. Yeah. In this class, I plan to do in this way. Yeah. For your midterm tests, I plan to give you 10 questions. Okay, 10 computation questions. Yeah, problem solving. Yeah, so not the concept questions. Concept question I will post as a quiz. Okay. Concept questions I will use a quiz to deliver that part, 10 questions. Yeah, as usual. That will be the part A of the midterm, part A, 10 questions. It's a quiz type. Yeah. Canvas, right. Yeah, Canvas. Still you have, more than 1 week to complete it. It's like a regular quiz, but I treat it, so I will use it as the part A of the midterm. Yeah. Part B, 10 questions, then in this classroom. Okay, yeah. So everyone must be, you need to come to the classroom. Yeah. So you need to do it. Yeah. All right. So I plan to give you 10 questions. Yeah, actually 10 questions, in 2 hours still, very hard for most of you. For most of you, very hard, 10 questions. Yeah. But I will give you, so here, after you come back after the spring break, March the 18th, Tuesday, I will give you the question types of those 10 questions. Okay? Yeah. So question 1, what's the type? All right? Because, yeah, let me think about it. Yeah, question types. Yeah. Probably I like to give you earlier, yeah, because that will be too late, right? Yeah. it's better to give you question types much earlier than yeah, because give you plenty of time to prepare. Yeah, it should be. Yeah, yeah. I should be post the question types at the beginning of the spring break. So I know some students, you may have the plan, but whatever the spring break, yeah. So I will give you the 10 question types at the beginning of the spring break, because you need to do preparation. Yeah. So you need some time to do preparation. Yeah. So the first question type, I'll give you example. Okay? Yeah. So the real question, similar type, just with different numbers. Yeah. Okay? Things like that. Okay? Yeah. Question types, I'll give you example. Yeah. The example I will use based on our homework assignments. Okay? 2 homework assignments. Yeah. Yeah. 1, 2, 3. Yeah. So I select 10 questions from 2 homework assignments. Okay? Yeah. So when you do preparation, so you can focus on those 10 question types. Yeah. All right. Yeah. But the real questions, the numbers, slightly different. Numbers different, yeah, but sometimes for the word problems, the conditions should be slightly different. Word problems, yeah, because I don't want to use the, only change the numbers for the word problem. That will be too easy. Okay? Yeah. So in that way, you are expected to complete those 10 questions in 2 hours on March the 20th, Thursday. Okay? Yeah? Yeah. Yeah. All right? So please, try your best to make arrangement. Yeah. Make your, study plan. Right? Yeah? So study plan. Yeah. 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 So that's what I want to say. Any question? So you can ask me a few questions if you have. Yeah. From both sides. Yeah. Yeah. All right. Yeah. Okay. Yeah. Yeah. So then in the review, number 18, because you already have the 10 question types. In that review class, so I may like to, because that class I want to use to help you. I want to use to help you on the for the midterm. Yeah. So on March the 18th, that day, I will go through those 10 questions. Yeah, but I will use because at that time I already completed the grading, so I will talk about the problems you have in those 2 assignments. Yeah. Homework number 1, number 2 assignments. Yeah. I will talk about that in homework assignments. Yeah. Then probably I can also give you a few sample questions. Yeah. Because review, I want to check your preparation. Well, because after you do the preparation, so then on Tuesday, so I will use a few sample questions to check your preparation. Okay? Yeah. Yeah. So that's the plan for Tuesday before the midterm. Okay? Yeah. Because it is very important. So we need to spend a lot of time, okay, to prepare for this midterm. Yeah. All right. Yeah. So let's move to what we left last time. Part B, somewhere in the middle. Yeah, I remember this delta function. Yeah. When we talk about this delta function. So we were here, yeah. This place, yeah, before that, yeah. This. Right. Yeah, so let me recall a little bit. Yeah. So this special function, delta function, Dirac's delta function, yeah, it's different from all the other functions we have learned so far because it is not a real function. Okay, it is not our usual function. Well, so we call it generalized function. Okay, generalized function. If you use the definitional function to check it, then it does not satisfy that standard definition. Okay, all right. But it is extremely important. Yeah. This function is extremely important, especially in math. It is important. In math, so in solving differential equations, it is very important. Yeah. But in engineering, it is also important because it can be used to model some special real-world phenomenon. Yeah. So we will see that. Yeah. So for that reason, so we need to define, something. It looks like it is not a rigorous math, right? Yeah. So in the history of math, many mathematicians, so they couldn't accept this special function. Yeah. 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 But after some period of time, because people can use this special type of function to solve many important problems. Yeah. Theoretical problems, application problems, then people become more and more, willing to accept it. Yeah, yeah. And no contradiction, right? Yeah, because after they apply this special tool, no contradiction. Yeah. Everything works perfect. Yeah. Then later, mathematicians, they develop some theory to make it rigorous. Yeah. So some special theory was developed, to support this kind of special functions. Yeah. All right. So that theory, so people call this kind of function distribution. Yeah. Because they don't want to use this function because it's confusing, right? So people call this type of function, actually the so-called generalized function, the formal name for it, distribution. That concept, distribution concept, okay? It's not a function. So it's a distribution. So then there is a definition for the distribution. Then develop the theory about the distribution. Then there is some rigorous mathematical theory related to the distribution concept to support this very powerful tool. Okay? Yeah. All right. Yeah. So although here in this class and in our textbook, so we didn't talk about distribution. Yeah. So we, because we don't want to go to the higher level math. Yeah. If you talk about distribution, quickly you jump to the much higher level math. All right. Then the formal definition. So here, delta of t minus a, yeah, two values, infinity at point t equals a. This value looks weird, right? Yeah, not normal. Yeah, because we know infinity is a symbol. Infinity is not a value. It is just a notation, symbol. Yeah. It's not a valid number. Infinity symbol, it's not a valid number. Yeah. Because here it is hard to put a valid number here. Yeah. So then just, here we treat it in a special way. So we allow, so you can put infinity there because we want to describe the meaning. Yeah. Describe the meaning. Yeah. Yeah. But infinity, although we put the symbol there, when you do the calculation, you should not use the infinity to do the calculation. All right? Yeah, because completely, messed up. When you use the infinity symbol in your calculation, you messed up. Yeah. Yeah. So it's just a visual sense. Yeah. So you cannot use in computation. Yeah. Then zero otherwise. So you can see it's very strange. If you want to imagine the graph, yeah. So it's very special. Yeah. All right. Okay. Yeah. So then, second, the property. The property here. This property, very important. The integral of this function from 0 to infinity. Yeah. Yeah. So definitely a should be greater than a. A should be greater than 0 here. Yeah. So here the a should be greater than 0. Otherwise, that peak, you have a special peak point. The peak point is out of the domain, right? Yeah. So because we want to cover, so we want the peak point located inside that range. Yeah. And we also know the integral, this integral represents the area. Area, yeah. So here, the area, yeah. Look at the area here, yeah. But you need to, stretch, here, skinny, yeah. Make it very skinny and stretch, to the extreme. Still, always area 1, but you make it longer and longer, yeah. So that's this property, yeah. Key property for this function, yeah. All right. So with this special function, yeah, generalized function, yeah, then we can, in our engineering application problem, we can use it to model some phenomena. Impact phenomena. One, here just a few examples. An airplane making a hard landing. Yeah, that force, right? Yeah, that special kind of force. So how do you model it? The best way you use the delta function to model it. Yeah. Another one. A mechanical system being hit by a hammer blow. Yeah, hammer blow. Yeah. That's that kind of force. Yeah. Another one, a ship being hit by a single high wave. Yeah. Yeah. All right. Yeah. So you can see the impulse of a force. Yeah. So these phenomena have the impulse type force. Yeah. So actions of forces, yeah. Mechanical, electrical. Yeah, also electrical. You have this impulse of a force apply over short intervals of time. Yeah, so very short. Yeah, the time interval. Yeah, very short. Yeah, fraction of second. Yeah, that long. Yeah, then this is a ideal representation. Yeah, because here you can see we do not use the specific that period. How long is that period, right? So we do not use that. Yeah. So from this delta function, you can see, we make that period, close to zero. Yeah. The short period of time, close to zero. Yeah. All right. Then, next, we need to develop some formulas. Mainly, we need to develop the Laplace transform on this special function. Yeah, it's a powerful tool. Yeah, all right. The properties, shifting property. The first property is shifting property. Yeah, all right. So that when we use a function, then multiply this delta function, but multiply the shifted version of this delta function. Shift a units to the right. Yeah. A, it's a positive number. Yeah. So here, a should be in the range, right, between 0 and infinity. Yeah. Otherwise, this peak, this delta, the peak point, is out of the range. Then you do not use it, right? Because the reason we use this, we want to use that peak point. That's the reason we want to use it. Otherwise, useless. Okay? Yeah. So we need to make sure the peak point is located inside our range or domain. Yeah. So whatever you call it. Yeah. All right. So then the integral, just the g function evaluated at that peak point. So this property, a very simple, basic property. But we need to prove it. Yeah. Mathematically, we need to prove it. Yeah. But when we prove it, we cannot use the, this definition of the delta function, because we cannot use infinity in our calculation. Yeah. So we need to go back to that FK sequence, remember? So how do we, study, represent this delta function? We use a sequence of F function, FK, that function. So we need to get there. Yeah. All right. So we need to consider this FK function. The FK function, remember that rectangle, skinny rectangle. Yeah. So here, the area. Yeah. So this is the FK function. This FK function, it is a valid function. Yeah. Normal function. Yeah. So we can do the calculation, but that K can change. When we do the calculation, we know K is non-zero. K is positive, greater than 0. But we can make that K approach to 0. And then we take a limit. That's the way we can do the calculation involving this delta function. All right, let's do it in that way. All right, so now let us use the FK function, because its value is 1 over K, but between this interval, from A to A plus K, that interval. So that when we calculate the definite integral, that constant, we can take it out. 1 over k is a constant. Okay? Yeah. Then, oh, yeah. Then, all right. So here, yeah, actually, yeah. Yeah, this thing, yeah. Actually, yeah. You know, to write it more rigorously, I like to write in this way, yeah, because this way, you know, jump too fast for you. Okay, how can you replace it? Yeah, yeah. Some people, you know, just replace it because in that short period of time, by approximation, they repeat it. Yeah. If we want to do it a little more rigor equals, let's take 1 over k out. Yeah. Then inside from a plus k, g of t. dt. Then we need this property. G function is a continuous function. This property we need to use. G must be a continuous function. Otherwise, we do not have this property. When G is a continuous function, then look at this part. If G is a continuous function, then G of t is close to G of a, right? In this small interval from a to a plus k. Yeah, very close. Yeah, continuous. Yeah. That's the definition of the continuous function. Why? How can you make it continuous, right? So this property, this is in the definition of the continuity. Yeah. All right. So G of t, we can make it approach to G of a, and we can make the error as small as we want. Yeah. That error, we can make it as small as we want. Yeah. So in that way, yeah. So then we replace. Yeah. You replace G of t by its approximate value. But the error is very small. Error is under control. Control, remember the epsilon delta, right? So in calculus, we use epsilon. That epsilon, we can make it extremely small, approaches to 0. Yeah. In that way, so you get a G of a. Yeah? Because basically this is a constant. You take it out, then upper limit number a plus k minus lower limit number a, you get a k. K and 1 over k cancel out. So you get G of a. Yeah. Yeah. So you get this shifting property. Right? All right? Yeah. Then Laplace transform. Yeah. When we calculate Laplace transform, we also need to use this fk function. Yeah. All right. The formula is Laplace transform of this delta function equals e to the negative as. Yeah. So let's prove it. Yeah. All right. Yeah. But first, when we prove it, take Laplace transform. First, we need to represent this fk function, yeah, using the Heaviside function. This u, yeah, Heaviside function. Yeah. Look at that. Yeah, Heaviside function. Okay. Yeah. From this graph, you see. Yeah. So it's a, the subtraction of two Heaviside function. Yeah. So that's this step function. Yeah. In this interval. Yeah. All right. Then. Yeah. We know the Laplace transform of Heaviside function is this formula we use. Yeah. All right. Then, by the linearity Okay, so we apply Laplace transform on fk function. All right. So then by the linearity principle, then we apply the Laplace transform of the Heaviside function, so we get this formula. All right. But in this formula, that k, we can control that k number. Okay? So we can make that k as small, as close to 0 as possible. Yeah, just make it close to 0. Okay? Then we take infinity. We take the limit. We take limit. Yeah. All right. So here we need to calculate the limit when k goes to 0. Okay? Yeah. How to calculate? Yeah. So to calculate it, yeah. So there are two ways you can calculate. The first way, L'Hopital's rule, right? The first way, you apply L'Hopital's rule. By L'Hopital's rule, you take derivative. Yeah. Here you treat k as variable because k goes to 0, right? K goes to 0, so you treat k as variable. S as constant. S never changes. So S is constant. So k is variable. And when you apply the L'Hopital's rule, it must be an indeterminate form. So here the indeterminate is 0 over 0, indeterminate form. Okay? Indeterminate form. You need to check the condition. Then you can apply L'Hopital's rule. L'Hopital's rule, yeah. So let me write here, based on the L'Hopital's rule, yeah. So here, yeah, because I need to show a formula later there. So I need to, yeah, let me use the, space here. K goes to 0, yeah. L'Hopital's rule. Equals the derivative with respect to k. K is a variable. So when we take derivative with respect to k, the denominator, that's easy. After you take derivative, it becomes s. The numerator, two terms. Derivative of the first term, 0. So it's gone. The derivative of the second one, apply the chain rule, negative sign, yeah, chain rule, all right? Remember, e to some function, then chain rule, so derivative of the exponent part, negative s, right? Yeah, because k is the variable, s is the constant. So derivative of it, the exponent, it is negative s, but you have a negative sign before this function, negative becomes positive. So you have s out. Then e to the negative ks. Yeah, that's derivative, right? So s cancel out. Right. Then this e function, e to the negative k times s. S is a fixed number, fixed constant, and it never changes. K goes to 0. Yeah, so the exponent goes to 0. E to the 0, that's 1. Okay? E to the 0, that's 1. Yeah. So this is by L'Hopital's rule. By L'Hopital's rule, you get this e to the minus as. Yeah. That's the first method. Okay, so here I review the L'Hopital's rule a little bit. Okay. All right. Second, Taylor series. Yeah, because we have Taylor series for the e function, right? Yeah. So let us use the, Taylor expansion. Yeah. The formula, Taylor expansion, e to the x equals, the series. Yeah. Then you plug in. Yeah. So here, let me write a few steps. Yeah. So let us look at the numerator. We apply the Taylor series of the E function. Yeah. 1 minus. Yeah. All right. So then inside the brackets, I use the Taylor series of this E function. 1 plus x, that is the negative ks, right? Then plus, now that is the high order terms. Let me just write another term, high order term, ks squared, and because those are the high order terms. Okay, all right. We know high order terms go to 0 faster than lower order terms, right? Faster, okay? Yeah. All right, so cancellation, the numerator, this numerator, one cancel out. The second term, negative ks, but we have a negative sign before that. So it is, let's write this way, equals ks, but plus high order terms, okay? High order terms, yeah, here. Little o of k. Yeah. Because the order is higher than this k. Little o, we know, when we take infinity, these higher order terms go to 0 faster than k. So here we use little o for simplicity. Yeah. Then, that's the numerator. Denominator ks, you can see denominator ks plus little of k over ks, then you make k goes to infinity, k goes to 0, then it is 1. Yeah, because this part is 1. The second part, little o, okay, little o of k over k, it must be 0. Yeah, infinity. Okay. Yeah. Yeah. So you use Taylor series. You can also prove the Laplace transform. Okay. All right. 2 ways you can use to prove Laplace transform. So we review our calculus methods a little bit. Yeah. All right. So after that, now we can apply these formulas. Yeah. B.3 examples with Dirac's delta function. All right. Mass spring system under a square wave. Yeah. Determine the response of the damped mass spring system under a square wave. Yeah. This is a square wave. Okay. Yeah. Yeah. So this part. Okay. The square wave, not this part. Okay. Yeah. Then the function. Yeah. The right-hand side square wave, that is the representation of the square wave. Now, our function, yeah, that's the driving force. Yeah. Then we need to find a response. The response means the solution. Yeah. So this response, that's y of t, the solution. We need to find a little y of t. Yeah. Yeah. Here we let us just apply Laplace transform, both sides. Initial values. Yeah. We need to use the derivative formulas. Yeah. So these 2 derivative formulas. Yeah. Because all the initial values are 0. Yeah. So you can see, all these terms all gone. Yeah. So the Laplace transform of y double prime, only one term, s squared times capital Y. Yeah. Laplace transform of y prime, one term, s times capital Y. Yeah. So then you plug in. Yeah. So you get s squared times capital Y plus 3s capital Y plus 2 capital Y. Yeah. Right hand side, yeah, we apply the Laplace transform of the Heaviside function. Okay, yeah, yeah. All right, now you can find capital Y of S in this formula. Next, then we need to, because the numerator two terms and each term is an E function. E function, yeah. So we have some formula. Yeah. So we consider capital F as the function without E function. Yeah, because we know E function by our shifting theorem, right? So we have shifting theorem. So we can take care of the E term. Yeah. So first we need to consider the version without E term. Yeah. Here we want to calculate the inverse Laplace transform of this F function. Yeah, because that's the denominator part. Yeah, numerator 1, the denominator we do the factorization. Yeah. Yeah. All right, so here I want to split. I want to split this fraction, decompose this fraction. Yeah. Most of you in this situation, most of you know you can use partial fraction way, right? Yeah, you can use partial fraction way. Yeah, but you need to do some work. Okay, quite some work on your scratch paper. Yeah. Here for me, because based on my experience, so I can split it. Yeah, I can use my observation to split it. Yeah, without using partial fraction way. Here, let me show you how do I split. Because it's a product of three factors, I need to split twice. I need to split twice. Each split, I want to work on product of two factors, not three factors. Three factor, we need to split twice. All right, so let me show you how do I split. All right, the first split, can you see this split? Can you see? Yeah. So you may feel a little hard. Yeah. Can you see? Oh, sorry. And 1/2. Okay. Yeah. Here I show you how do I split. All right. Because the reason we know three factor split, we need to use two steps to do split. When I do split here, I need to take 1 over S plus 1 out, yeah? You know, this whole factor out. Inside the second parenthesis, S times S plus 2. Right? Yeah? So the first parenthesis, I do not touch it. Yeah. Yeah. I keep it, the first parenthesis. Second parenthesis, I split it. I split it. Okay? I split it. Yeah. Second parenthesis. So the first parenthesis still S plus 1. But the second parenthesis, yeah, let me use a bracket. Okay. I split it 1 over S minus 1 over S plus 2. Yeah. Can you see? Yeah. Common denominator, numerator S plus 2 minus S2. 2, yeah. 2, it's because our numerator is 1. You have 2, no problem. You multiply 1/2 to cancel out that 2. Cancel out that 2. Okay? Yeah. All right. So this is how we get here. Okay? Yeah. Yeah. How we get here. So 1/2 times 1 over. So the first. Yeah. You can see after the first split, each term, the numerator two-factor form. Then let's do another split. Right? Let's do another split. Yeah. All right. 1 over S times S plus 1. We do the split like this. 1 over S minus 1 over S plus 1. Yeah. By our observation, we can see it quickly, right? Yeah. If you want to ask me how do you split in this way, yeah, by experience, by observation. Okay, I know the product of two factors, Yeah, we just write two fractions, 1 over the smaller factor. S is smaller than s plus 2, right? 1 over the smaller factor minus 1 over the larger factor. Okay? Yeah. Yeah. But the numerator is not 1. We need to multiply appropriate constant number to make it a 1. Yeah. That way. So this is first split of the first fraction. Split of second fraction using that same way. Okay? The smaller factor, the larger factor, 1 over the smaller factor minus 1 over the larger factor. Yeah. But the difference of these two factors is 1, so we do not need to multiply any constant number. Okay, in this way. Now, you go back to the original place. So f of x, you get a 1 over 2s. 1 over s, yeah, because you have 1 over s plus 1, 1 over s plus 1, two places, adding together you have 2 and 1/2 cancel out. So 1 over s plus 1. The second 1 over 2 times s plus 2. Yeah. After this decomposition, we are ready to calculate the inverse Laplace transform of the capital F function. Inverse. Yeah, 3 terms, but we need some basic formula. Yeah. So 1 over s, the inverse Laplace transform of that 1 over s formula, yeah, by the linearity, that we need that formula. Okay, formula is 1. Okay, inverse Laplace transform. So inverse this direction. 1. Yeah. All right. So first term. This should shift version, yeah, because also shift version, right? Yeah, we need to use, yeah. Shift version, a is -1, a is -2. Okay, yeah, all right. That 1/2 times 1 minus e to the at, a -1, so that's why e to the -t. Plus 1/2 times e to the, this time a is -2, so e to the -2t. Yeah. That's the little ft, yeah. Little ft function. So you put it aside, okay? Yeah. You need to use it later, so you put it aside. Yeah. Then we need to work on the e term. In numerator, there are 2 e terms, right? We need to, yeah, remember? So this is capital Y expression. Yeah. We find the f part, but next we need to take care of those 2 e terms. Yeah. Those 2 e terms, we apply this formula. Oh, sorry. This is our second shifting theorem. This is our second shifting theorem. All right, so then inverse Laplace transform, this is, we separate, yeah, 2 terms, yeah. Each term, f minus a, yeah. The first term, that a is 1, right? Yeah, because, negative as. The first term, a is 1. Second term, a is 2, okay? A is 1 first term. A is 2 second term. Then let's just plug in. Yeah. Yeah. First term, little f, yeah. Use a equal 1. Second term, yeah. And the little f, we know it. Okay? Yeah. If you want to, copy it another time, replace, then it's okay. Yeah. Here, I didn't do that. Yeah. Yeah, if we want to do another step, we can do it. Okay, all right. So 1/2 minus e to the negative parenthesis t minus 1. Okay, yeah. Plus 1/2 e to the -2 t minus 1. Okay. Yeah. But that's the f part, right? That's the f part. And then you need to multiply the u part. Okay? Then minus, another, right? Yeah. Just copy carefully if you want to. Yeah, otherwise, you leave it there. It's okay. Yeah. Leave it there because we know how to do it. Yeah. The last step, very simple. Yeah. Very simple. Yeah. All right. Yeah. So that's the way but this is Heaviside function, right? Yeah. So it's not the, delta function. Yeah. Yeah. Let me look. Oh, yeah. I don't have enough time. Yeah. All right. So let's take a 10-minute break. After that, so we will quickly. Yeah. We just have another example. We will quickly finish part B. So then we will start part C in our second half.